Good afternoon, everyone. Today, I want us to discuss a semiconductor device, which is a diode. Now, what is a diode? You will see that when you define a diode, it is defined as a component that allows current to flow in one direction. A diode is defined as a component that allows a current to flow in one direction. Now, a diode, it is symbolized, or the symbol which is used for a diode, it is this symbol here. Now, with the symbol, it consists of two parts. You will have the anode part, which is the positive side of the diode. Then you will have the cathode side, which is the negative side of the diode. The positive indication, the negative indication. Now, as I've already explained to you, this is a one direction or one directional component. So which means you need to make sure that the positive side of the battery or the positive side of the source is connected on this part. The negative side of the source is connected on the negative side of your component. Then it's going to allow the current to flow in one direction. Now, that simply means that if the current is flowing within this component here, then you have forward bias, this component here. So which means it has got two biases. You have got the forward bias and you have got the reverse bias. Now, when you reverse bias, which means now this component, it's no longer functioning. Now, how do we indicate these? You will see that with this component, you have got three types of models. With this component, you have got three types of models. You have got what we call an ideal model. You have got what we call a complete model, and we have got what we call a practical model. Those are the three models that you find within this component. Now, if you go to your textbook, then you must go and check how do they define an ideal model, how do they define a practical model, and also how do they define a complete model. Now, let's see how this component or how the properties of this component exist. Now, if you connect this component into an electrical circuit, then you will see that I will have a source, which is your DC source, the positive side, the negative side. Then I will have a limiter, which is your resistor, your RL, which is your limiter. Then I will have this model here, which is your diode model. Now, this is your VDC or your supply voltage. Then you will know that with the electrical circuit, we are looking at your conventional current, which means your current is moving in that direction there. Now, if I want to see the properties of this component, then it goes and says, which material is it used? Which material is it used to construct this component here? You will see that we've got two types of materials which are used in order to construct this component. Now, we have got what we call a germanium material, and we've got what we call a silicon material. A germanium material or a silicon material. Now, these two materials, they differ according to the voltage drop that exists within this component at a certain condition. They differ within the voltage drop that exists in this component at a certain, in a certain condition. Now, with the germanium, which is your GA, you will see that the voltage drop during forward bias, which means now it is allowing the current to flow. During forward bias, then it says the voltage drop that can exist there, it is 0.3 volts. Now, with the silicon material, the voltage drop that can exist within this material, it is 0.7 volts, which means you need to be very careful. When the question asked, when the question asked, which diode or which type of material is it used for that diode there? If it is a germanium material, then we know that it is a 0.3 volts that will be established within that component. But now, during forward bias, if it is a silicon, it's going to be 0.7 volts during forward bias. Now, if I apply the voltage here, I must apply the voltage of which this voltage, it must make sure that this component must be able to switch on. And when this component it is switched on, then it is on a forward bias mode. But now, if it is on a forward bias mode, then we go and check, is it an ideal model? Is it a complete model? Or is it a practical model? Now, you'll see that in most cases, as how it has been defined, it's either they will say to you it is an ideal model or it is a practical model. Now, those are the most two common use models that you come across. These are the two common methods that you come across. It's either it is an ideal model or it is a practical model. Now, if I say this to you, if I say to you, what is the voltage drop that you find across this component during an ideal model? During an ideal model, you will see that when you look at how they define an ideal model, then they say during forward bias, this component acts as a closed switch. During forward bias, this component acts a closed switch. It simply means that when I measure the voltage across this component, I'm going to measure V of the diode 0 volt, because it's just a normal wire whereby, or it's just a switch that acts as normal wire whereby the current can be able to flow. So which means you don't have the voltage drop that can exist within this component of 0.3 volts or 0.7 volt. But now, if it is used as a practical model, then you will see that with the practical model, you will have your voltage, or you will have your battery symbol, and then you will have. That's why I said you must go and look at your textbook or your notes, whereby how do they define the practical model, how do they define the ideal model, or how do they define a complete model. So which means during forward bias, which means you need to be able to establish the voltage, which is according to the material, it must exceed. If it doesn't exceed, which means this switch will keep on being on an open state up until it has measured the 0.3 or it has measured the 0.7 volts, which means then you will have a closed switch. Then when you measure across this component here, you're going to measure your germanium or your silicon material. It's either a 0.7 volts or a 0.3 volts. But now, that depends on how did they specify this? Did they specify this idea, or did they specify this as a model? Okay, now, if I get an example just to illustrate how this component, or how do you look at the properties of this component. Now, let's say for an example, you are given a circuit whereby your circuit connection, you are given an example whereby your circuit connection, it will have a DC source, Now with the DC source, you will have a resistor, then you will have a diode, then ground, let's say this is 4 volts. Then here you'll have your resistor, let's say it's 10K. This is just for an example. Then you have another resistor there. Then let's say that is 10K also. Now, and this diode, it is defined as, it is a germanium diode. It is a germanium diode. Now, if one were to ask you, you must calculate the voltage drop across your 10K resistor. One said you must calculate the voltage drop across your 10K resistor. Now you will see that for you to be able to do that, then if you look at these two components, your diode and your resistor, both of these components, they are connected in parallel. So now we go back to extra notes. We know that when it comes to electrical circuit, you have got a series connection and you have got a parallel connection. Now the series connection comes with its own characteristics. The parallel connection comes with its own characteristics. Now, if I look at this connection here as a parallel connection, which means now I must recall what are the characteristics that exist within a parallel connection. You will see that on a parallel connection, it says the current must split, but the voltage remains the same. The current must split, but the voltage remains the same. Now, if the voltage remains the same, because this component is a semiconductor component, then we'll go and check if this voltage of 4 volts were compared to the voltage drop that can exist within this component during a bias. Now, as a one-directional component, it simply means that the voltage of this component, when this component has switched on, as a germanium material, which means it must be 0.3 volts. Now, if I look at 0.3 volts, I look at 4 volts, I will see that 4 volts is bigger than 0.3 volts, which simply means that this component, it will be able to switch on. This component will be able to switch on. So which means the maximum or the allowance of the current that is going to flow within this component with the magnitude of that, then it's going to allow that component to switch on. Now, if this component switches on, then according to your understanding of the characteristics that exist within a parallel circuit, then the voltage that you're going to measure across these two nodes, it is going to be the same voltage which already exists of 0.3 volts, which means V of this node here, V of this node here, in this case we can say V up, V of this node here, it is going to be 0.3 volts, irrespective of whatever that you see there, because already this one is coming with a barrier potential. Now that barrier potential was established during the process whereby this component here, because it is a practical model, it will consist of an internal voltage, which is your forward or your barrier potential voltage, and a switch. Now, is that switch open or is that switch closed? And according to the definition of this component, which is a diode, it says this component or whatever that exists within this component here, according to the switch, it must reach a certain magnitude of the voltage so that this can be a closed switch. Now, the moment it becomes a closed switch, which means now your voltage is 0.3 volts, which means when I measure there, I'm going to measure 0.3 volts. So it doesn't matter how you look at your diode circuit. Always remember, your input voltage always needs to be bigger than the voltage that will cause this component to be on a forward bias mode. But now, if it doesn't reach that, which means this component will be on an open switch. Now, if it is an open switch, which means now it is on a reverse bias mode. Now, if it is on a reverse bias mode, then it is not allowing the current to flow. And if it is not allowing the current to flow, which means whatever that we're going to measure here, we are going to measure according to your KVL, the Kirchhoff voltage rule. Then the voltage drop across this component and that component must be the same as that voltage there. Now, what I want to emphasize here is that when you look at this component, because it is a one-directional component, it allows current to flow in one direction. It needs to be a forward bias, or it needs to be on a forward bias mode. So now if it is on a forward bias mode, your input voltage must always be bigger than the switching voltage. And the switching voltage is either a 0.3 volts or a 0.7 volts. Now, if you go back to your textbook, then you will go and check on the characteristics of the voltage and the current characteristics. Then it indicates to you when you get to see this as a forward bias and when you get to see this as a reverse bias mode. Okay? Now, then it goes and say, this component can work in different application. This component can work in different application. Now, the first application that I want to discuss with you, it is the application of a clamper circuit. The application of a clamper circuit. Now, with the clamper circuit, then you will see that your circuit, it is a circuit whereby you have got a source, which is your AC source, with a clear definition on how you're looking at this source of yours. And we know that in most cases, when we look at this source, we will see that it needs to be a peak voltage. It needs to be a peak voltage. Now, if I give the definition here, I said the V peak of this, which means now you're having 10 volts peak. That is your AC source. Now, if you look at this as a peak voltage, then we will have a component, which is your capacitor component here. Then you will have your diode component. Then you will have your resistor component. That is the magnitude of your circuit. Now, with this component, we indicate that is the positive side of this component, that is the negative side of this component here. And we must bear in mind, we need the definition of these. Is it an ideal model? Is it a practical model? Or is it a complete model? Preferably ideal or a practical model. In this case, that is your practical model. Then we say this is your silicon diode. That is your silicon diode. Now, the moment we see the silicon diode, then at the back of the mind it says, oh, if it's a silicon material used, which means during forward bias, with forward bias, which means now it is allowing the current to flow. And if it's allowing the current flow, which means the current is flowing in that direction there. That is on your forward bias. Then the establishment of the voltage during forward bias with respect to the input voltage, so that this component can switch on, which means the voltage here must be 0.7 volts. 0.7 volts. If this indeed exists, because the magnitude of the connection in terms of the electrical circuit, which is your positive, sorry, which is your parallel circuit, therefore, this component automatically, it is going to exist within that magnitude of the voltage there, which is 0.7 volts. Let's say this one, we say that is 220 microfarad. That is the magnitude of your capacitor. Let's say this one is 220 kilo ohm. Now, if I've got this magnitude of the circuit, then with the capacitor, this one is the positive, that one is the negative. Now, if we look at how this is going to conduct, then it goes and say, whatever that you see with respect to this, you need to make sure that this component, it is on a forward bias mode. Now, if it is on a forward bias mode, which means now it is allowing the current to flow. If it's allowed the current to flow, which means my V out is going to be 0.7 volts. My V out is going to be 0.7 volts. But now, if it is of a clamper circuit, now then we're going to say, how do we find the magnitude that can exist within this circuit? What will be a clear description of this circuit here? Is it a clamper circuit positively, or is it a clamper circuit negatively? Is it a clamper circuit positively, or is it a clamper circuit negatively? Because with a clamper circuit, it's either it clamps this on a positive cycle in terms of your Cartesian plane, or does it clamp it on the negative side with your Cartesian plane? That is quadrant 1 and quadrant 4. Quadrant 1 and quadrant 4. Now, if I have this type of circuit, now I need to check, is it going to move it upwards or is it going to move it downwards? Now, if I look at the mathematical algorithm of these, or the mathematical analysis of this, then it goes and say, I will have to go and check. My positive is there and my negative is there. If my positive is there, my negative is there, which means when I look at my input, I'm going to look at the input in this manner. I'm going to look at the input from 0, alternating all the way positively, then back to 0. Then alternating all the way negatively, then back to 0. It simply means that here I have got maximum peak of 10, and here I've got maximum peak of minus 10. I've got maximum peak of 10 positive, minimum peak of minus 10 negatively. Now, this signal, is it shifted upwards or is it shifted downwards, but without tempering its original shape? Shifted upwards or downwards without tempering its shape. Now, for you to be able to analyze this type of a circuit, which is a clamper circuit, then you're going to say, the first thing that I need to do, I need to go and define a reference point. I need to go and define a reference point. The reference point in your original circuit, the reference, your V ref, is 0. Your V ref, it's 0. Now, because you have got this nature of connection, which means it's either it's going to retain an original reference or it will have a new reference. Now let's go and see. Now if I do this, I will do this following what we call a KVL, Kirchhoff voltage rule. Now let's look at the direction of the current flow. That is the direction of your current flow. That is according to the KVL. Now, then I will go and say, how do I look at this? You check your arrow is pointing how. You will see that your arrow is pointing in that direction there, which means it's going on a clockwise direction. Now, if it's going on the clockwise direction, how does it look at this magnitude here? You will see that it looks at this magnitude of the input from the negative side. When it looks at this magnitude from the negative side, which means here your V input, it will be a positive V input. That is according to the KVL. Then when you continue with the movement of this, you will see that now it looks at the capacitor. At what? It looks at the capacitor at the positive side. If it looks at the capacitor on the positive side, which means your magnitude, it is minus V of the capacitor. Minus V of the capacitor. Now, if that is minus V of the capacitor, then when you continue with this, now remember these two components, I just want you to bear in mind, these two components, they are what? These two components, they are parallel to each other, which means whatever voltage that I see here is the same voltage that I see there. Because of the magnitude of these and your barrier potential, already this voltage is bigger than that one, which means that component is going to switch on. And if it switch on, which means it's 0.7 volts. But now, if I am looking at this 0.7 volts, how am I looking at it? Already, it is what? That is the positive side, which means if that is the positive side, also that one is going to be minus V of the diode is equals to 0. Now, what magnitude am I looking at? It simply means that now I am looking at the magnitude of the voltage that will allow this component to charge on its full scale. Now, if I look at this continuously, then I'll say my V in, I know. What is my V in? My V in during this as a forward bias. I want you to understand this. During this as a forward bias, it will forward bias when you are looking at the positive cycle. If you're looking at the positive cycle, which means here it's going to be plus 10 volts. Plus 10 volts minus your VC minus. Here on this side, it's what? It's 0.7 volts minus 0.7 volts is equals to 0. Manipulation of formula, which means now your VC, it is 9.3 volts, which means that's your reference point. Now, if this is your reference point, then you will go and say, what was the initial voltage that I came across? Because the moment this component was connected so that it can allow the current to flow within this component here had to go and check, this one is bigger than the voltage that can be established there, which is 0.7 volts, which means I had a 0.7 volts there. Now, the first establishment of the voltage, it becomes your either your maximum or your minimum turning point. Your maximum or your minimum turning point. Now, the voltage that you established here was 0.7 volts, but it was a positive 0.7 volt. Now, if it is a positive 0.7 volts, then you will see that this component here, or this magnitude of the graph. It is going to be a magnitude of the graph that will have, is going to be the magnitude of the graph that will have a maximum turning point of 0.7 volt. A maximum turning point of 0.7 volt, which means here we establish if it's either a maximum or a minimum. We establish if it's either a maximum or a minimum. Now, in this case, it is positive, which means that is going to be your maximum. Now, if that is your maximum, the next establishment of the voltage, it is your reference voltage, which means now your reference voltage, in this case, because you are charging the capacitor, because you are charging, you are storing charges, but the value that you find here, it is positive, and this must be your reference. This must be your reference. If that is your reference, and that is the maximum turning point, which means this reference voltage here, when I look at it in terms of the graphical explanation, when I look at it in terms of the graphical explanation, which means this voltage here, it is minus 9.3 volts. It is minus 9.3 volts, which means now here, somewhere along the line, I have got minus 9.3 volts. Somewhere along the line, I've got minus 9.3 volts, which means I no longer have a reference of what? I no longer have a reference of 0. Now I've established a new reference, which is minus 3.9 volts, which means now my graph needs to start from there. If my graph starts from there, which means it's going to go all the way up, turn there at 0.7, then back to that point there. Now that is during your positive cycle. That is during your positive cycle. Now, because this is an alternating, which means now I am looking at this in terms of now this is moving within that magnitude here. Now I'm looking at this moving within that magnitude there, which means on the negative cycle. Now, what happens on the negative cycle? Which means I no longer have positive, negative, but I have got negative, positive. I've got negative, positive. Now, if I've got negative, positive, then you will see that now the current is moving in that direction there. Now the current is moving in that direction there. If the current is moving in that direction, what's going to happen? If the current is moving in that direction, what is going to happen? You will see that now when the current is moving in this direction, it's going to force this component to go to reverse bias. It's going to force this component to go to reverse bias. If this component goes to reverse bias, which means there and there, we no longer have a current flowing in this component here, which means that is just an open wire. If that is just an open wire, then now your current is moving within this component here, not looking at this. Your voltage of your V out, I need to follow your KVL. Now, if your voltage of the V out, you need to follow the KVL. Then I'm going to say, the KVL, it is established in this direction. If the KVL it is established in this direction, then I'm going to say, this, it's looking at this source, not from the negative, but from the positive, because the cycle has changed. If I'm looking at this from this side, what will be your input? You will see that in this case, now your output, now the arrow is facing the positive. If the arrow is facing the positive, which means now it's minus VE. Now it's minus VE. in. If it is minus V in, then you continue with this. Here, it's looking at positive, which means it's minus VC. When it continues with this, when it looks at that one, also it is positive, which means it's going to be minus V out, which is equals to 0. I hope up to so far we are together. Now, if I look at this establishment here, if I look at this establishment here, then you will see that here is going to be minus 10 volts, minus 9,3 minus V out is equals to 0. Then V out, the subject of the formula, which means now your V out now is given as minus 19,3 volts. Your 19,3 volts, then you will see that now your cycle is moving in that direction there. So which means now you have got this as 19,3 volts, but minus 19,3 volts. You will see that your shape didn't change, only the position of these has changed. Your shape didn't change, only the position of this changed. It's either it has moved up or it has moved down. But now looking at the magnitude of this, automatically you will see that this, it has moved what? It has moved downwards. If it has moved downwards, then it becomes a negative clamper circuit. So which means when you define this, then you'll say that is a negative clamper circuit. Only if you have defined it. Only if you have defined it. Now, the definition can be established in this manner. The definition can be established in this manner. The first thing that you need to do, you need to go and check with the voltage that is used to energize the flow of current. With this component forward biased, what is the output voltage? Then you will see it's either a minimum or a maximum. Maximum turning point or a minimum turning point. That is your initial stage. If you come across these as your first V out, as minus 0,7 volts. Your first V out as minus 0,7 volt. Just know that these component is going to move upwards. If it's positive, it's going to move downwards. Negative is going to move upwards. Positive is going to move downwards. Then it's either a positive clamper or it's either a negative clamper circuit. Cut.